All right, lastly, I want to go over this slide here and just kind of explain what's going on here. This is a theorem. It says differentiability implies continuity. Let f of x be a function and a be in its domain. It's a crucial piece there. If f of x is differentiable, in other words, it has a derivative at a, then f is continuous at a. So we want to show this. We want to show that f is continuous at a, which what I put up here in the corner are the conditions for something to be continuous. So we're ending this presentation where we started during our full lecture here on this slideshow. We have to be able to meet these criteria, okay? So the first piece is implied. F of a is defined. It's defined by the way f is defined. So f of x is a function and a is in its domain. So that means f of a is defined. Okay, so we're really left with needing to show that the limit of f of x exists, which you'll see this statement over here. And so we're going to go through some steps to not only show that it exists, but at the same time that it is equal to f of a. So number 2 and number 3 are done simultaneously, and a is from a given, and the way f of x is defined to begin with, right? So we're going to start with this statement, and we're going to show that this exists and that it is equal to f of a based on this hypothesis that f of x is differentiable. So we start with this hypothesis, then we're going to show that f is continuous by demonstrating that it meets these two conditions. Okay, so this is just a restatement of the hypothesis that f of x is differentiable at a, while just writing out what that means, that f prime of a is the limit of f of x minus f of a over x minus a. So we know that the derivative exists because we're stating that as a hypothesis. All right, so the limit of f of x, what is that? Well, the limit of f of x, what we do is, so notice that we're trying to get to the condition over here. This is what we're trying to get to. And once we get there, we not only show that it's equal to f of a, but that it exists. Okay, so the rest is just a use of algebraic tricks. They're tricks that don't necessarily come obvious to you. And this is where mathematicians would show their creativity. So what did we do? What did somebody do to prove this? Well, they subtracted f of a plus f of a. Basically, you're adding nothing, right? If you take something away and then add it back. And in the next step, what you're doing, or what is being done, is, it might have been easier if I had to understand it, but if we had written x minus a over x minus a kind of together, and then you see, well, if you multiply by 1, basically, you're not changing the equation. But that's what's happening here. You're multiplying by x minus a over x minus a, which is basically 1. And so you really haven't changed anything. You've added a 0 and you multiplied by a 1. And then you're going to use limit laws, which allow you to break this up into essentially three pieces. So you can take this product and then break this product up into two pieces. You have a sum, so you're breaking that up as well, and that's just using limit laws, some basic limit laws that we looked at when we met a week ago. And this is defined, right? We know what this is. If you look up here, it's the derivative of f at a. For this piece, if you plug in an a, you get a minus a, which is 0. So that's where that 0 comes from. And so anything times 0 is 0. So this whole piece is going to go away. You're only left with a limit of f of a, which now this has become a constant, right? So no matter what x is approaching, the limit of a constant is the constant. And so there you go. You've shown that f of a is, you've shown that the limit exists, and that limit of f of x is f of a. And so we are able to arrive at our conclusion. And that is where week 4's lecture will end.